Hello and welcome to the module x86 64-bit assembly language crash course. In this module, we are going to learn the fundamentals of x86 64-bit assembly language for Linux. This module is designed and created for those who want to get familiarity with x86 64-bit assembly language and GDB debugger. If you are already familiar with 64-bit assembly language and the basics of GDB, you can feel free to skip this module and jump directly into the next module. Having said that, remember this is not a complete assembly language course. We do not want to push you into complex concepts such as exploit development and writing shellcode without giving you enough basics, and that's exactly the reason why this module is created. So the idea here is for you to get familiar with some commonly used assembly instructions and how you can use GDB to understand what's happening in programs written in assembly language. By the end of the section, you will be familiar with common assembly instructions and debugging the programs using GDB and Jeff. If you have Jeff installed, you do not need to type some commands that are commonly used while using GDB. So let's get started. Hello and welcome to the module x86 64-bit assembly language crash course. In this module, we are going to learn the fundamentals of x86 64-bit assembly language for Linux. This module is designed and created for those who want to get familiarity with x86 64-bit assembly language and GDB debugger. If you are already familiar with 64-bit assembly language and the basics of GDB, you can feel free to skip this module and jump directly into the next module. Having said that, remember this is not a complete assembly language course. We do not want to push you into complex concepts such as exploit development and writing shellcode without giving you enough basics, and that's exactly the reason why this module is created. So the idea here is for you to get familiar with some commonly used assembly instructions and how you can use GDB to understand what's happening in programs written in assembly language. By the end of the section, you will be familiar with common assembly instructions and debugging the programs using GDB and Jeff. If you have Jeff installed, you do not need to type some commands that are commonly used while using GDB. So let's get started. Let's start writing some simple assembly programs using 64-bit assembly. I have a directory called x86_64 in my home directory. Let's navigate there. And inside this directory, I'm going to create another directory called ASM. And let's navigate to ASM directory. And let's create a new file called move.nasm. Here it is. I'm using Vim here. You can use your favorite text editor. And let's start with a directive called global, which tells our linker where the entry point of this program is. So I'm typing global space _ start. So we are basically specifying that the entry point of this program is _start. And let's start writing our actual code within this entry point, which is _start. So let's type _start : and this is going to be our entry point. Now let's begin writing some move instructions. Let's begin by writing a move instruction to move the value 8 into register RAX. We can do that by typing move RAX, 8. We can also move hex values into the registers. Let's try moving hex A, which is decimal 10, into RAX. Move RAX 0xA. In the first instruction, we are moving decimal 8, and in the next instruction, we are moving hex A. We are telling the program that we are moving a hex value, that's 10, by prepending 0x to A. Now let's try to move the value of a register into another register. For instance, we have the value of hex A in the register RAX. Let's try to move that into the RBX register. So I'm typing move RBX, RAX. There is another type of move instruction which will essentially move the value which is pointed by the address of a register. Let's see one such instruction. Move RCX, RSP, which is surrounded by square brackets. It will try to pick the address of RSP and it will move the value that is pointed by this RSP register into RCX. Now it may sound confusing, but let's try to debug this program using GDB in a moment and you will understand what I mean. Okay, that's pretty much it. We can now save the program. I'm typing Ctrl C and :WQ so the changes will be saved. Now let's use NASM to assemble this program. So I'm typing NASM move.nasm -o move.o -f elf64. We are specifying that it's a 64-bit program. I'm hitting enter. Now let's link it using ld move.o, which is the output from the previous command, and let's produce the output and let's name it move. Let's hit enter. So move is going to be the final binary. To be able to examine the registers and the values that are being moved into registers, let's open this program using GDB. So I'm typing gdb./move. If you notice, we are seeing a Jeff terminal because we have installed Jeff for GDB. This makes our life so easy during exploit development. Trust me, you're going to love it by the time you reach the end of the course. Now let's set up a breakpoint at the entry point of this program. If you remember, our entry point is _start. So I'm typing break space _start. I'm hitting enter. If you notice, there is a breakpoint set at this particular address. Now if we type run, the program will run and it will pause the execution at the entry point because we did set up a breakpoint. I'm hitting enter and look at this. Currently, the next instruction to be executed is this. And if you notice, there is a breakpoint, so the execution is stopped. Now, there are few things that we would need to observe in this output. Number one, code. If you notice, this is the code section. You can see it here. It is highlighted. And these are the instructions that are going to be executed when we run this program. So this is the area where we are going to notice all the instructions that get executed. So the next section is stack. This area shows the stack. We are going to use it extensively later in this course, so it is good to know where the stack is in our output. After that, let's take a look at registers. If you see this, these are the registers. Once again, remember, we are going to make extreme use of these registers, stack, and the code section. So it is good to note where they are in your Jeff output. Now, within these registers, let's take a look at the RIP register. If you notice, the RIP register is pointing to this address, which is ending with 401000. So let's scroll down. And if you notice, this is the address. And as you can see, this is the beginning of our program, and this is the next instruction to be executed. And if you look at this address, this is same as what we have just seen in the RIP register. What it means is RIP always holds the address of the next instruction to be executed. One interesting thing to note here is that the first instruction has the register EAX instead of RAX. This means some optimizations have been made by the assembler. Now let's try to execute this instruction and see what happens to the value of RAX. Before that, let's check what we have in RAX register. If you notice, RAX currently has 0, and we are about to execute the instruction which is going to move the value 8 into the register RAX. So let's type SI, which stands for single step, which means execute one instruction. Okay, so let's hit enter and see what happens to RAX register. I have executed one instruction. If you notice, this is the next instruction to be executed now. But before executing that, let's take a look at the RAX register. If you notice, the value 8 is now placed in RAX register. Alright, that is expected. Now let's type SI once again and see if this value 0xa is going to be moved into this register. So let's type SI. Let's once again examine RAX register and look at that. The value 0xa is now placed in RAX and the value 8 is overwritten. And the next instruction to be executed is move RBX, RAX. This means whatever the value that we have in RAX is going to be moved into the register RBX. So let's first check what we have in the RBX register. Here it is. Currently, RBX register contains the value 0 and the RAX register contains the value 0xa. So once the instruction gets executed, this value 0a should also be available in RBX register. Remember, move is not literally moving, it is basically copying. So we will still have the value in RAX register as well. So let's type SI. Now once again, let's examine the registers. Look at that, the register RBX is now holding the value 0xa. Alright, now if you notice the next instruction, as I mentioned earlier, it is going to move the value that is pointed by the address of RSP into RCX. So let's first check what RSP is. RSP or stack pointer is always going to point to the top of the stack. If you look at this, RSP is currently pointing to this particular value. This is the address of the top of the stack and it is pointing to this particular value. So currently on the top of the stack, we have the value 1. So if you type SI, which is a single step, we should see this value 1 in register RCX. So let's see if our theory is correct. First, as usual, let's once again check what RCX currently contains. As you can see, it contains the value 0. So I'm just going to type SI. And let's once again go back and check what RCX has. As you can see, it now contains the value 1, which is actually taken from the top of the stack. Well, that's the end of it, and this is how move instructions work in 64-bit assembly language. Now let's discuss how we can use subregisters. Let's begin by creating a new file called subregisters.nasm. And as usual, let's start with our global directive. Global space underscore start, and let's specify our entry point here. Now once again, we are going to use the move instructions, but instead of using a register like RAX and RBX, we are going to try to use the subregisters of those registers. So let's get started. First, let's use move AL, 10. This is one of the subregisters from RAX. Let's also use move AH, 20. Let's also use move AX, 30. Let's use move EAX, 100. Finally, let's use move RAX, 200. If you notice, we have used pretty much every subregister from the RAX register. This is just to demonstrate that we do not have to use the full 64-bit register if you just want to store some smaller value into a register. So let's save the file and let's use NASM to assemble this program. NASM space subregisters.nasm -o subregisters.o. Once again, the format is going to be ELF64. Let's hit enter. Now let's link it using LD space subregisters.o space -o subregisters. Let's hit enter. Now, like we did earlier, let's open up this program using GDB. So I'm typing GDB space subregisters, and let's once again set up a breakpoint at the beginning of the program, which is _start, and let's run the program. Once again, if you notice, we have 0xa, which is being moved into AL register. Ultimately, even if you are moving it into AL register, it is going to be saved in RAX register because AL is a sub-register from RAX. So let's quickly check what we have in RAX register before executing this instruction. If you notice, currently RAX register contains the value 0. So let's type SI and let's see what happens. There you go. RAX register now contains the value 0xa. Now let's try to execute the next instruction, which is moving hex 14 into the register AH. I'm hitting enter once again, and look at that. Now AH contains the value 14 and AL contains the value 0a, and both of them together are forming this value. Now let's move 0x1e into AX register. So I'm typing SI once again. If the previous command that you have typed is SI, you don't have to type SI once again. You can just hit enter. It is just going to take SI from the previous command. So I'm hitting enter without typing anything so that it will do a single step automatically for me. I'm hitting enter. Now the value hex 1e should have been moved into the register AX. Let's observe RAX once again. Look at that, 0x1e is now moved into the register AX. Now the next instruction to be executed is move the value hex 64 into EAX, which is decimal 100. So let's hit enter and let's observe RAX once again. As you can see, we have hex 64. Finally, we are moving decimal 200 into EAX register. Once again, if you notice, when we were writing this program, we used RAX register, but assembler has made some optimizations and the RAX register is not used. Instead, the subregister EAX is used here. So let's type SI once again and let's examine RAX register. As you can see, the value hex C8 is moved into RAX register. So this is how we can use subregisters. Now there is one interesting thing to note about when we are using subregisters. Let me quit GDB and let's type object dump and let's dump the disassembly of the program that we have just written, which is subregisters, and let's type -m Intel so that the instructions will be shown in Intel syntax. Okay, so let's hit enter and look at that. If you notice, the instructions which are having the registers like EAX and RAX with smaller values are having null bytes in the disassembly. However, when we used subregisters, they did not produce any null bytes. So making use of subregisters is a great way to avoid null bytes when writing shellcode. We are going to discuss these concepts once again when we write shellcode, but since we came across the concepts of using subregisters, I just wanted to quickly show you this. Alright, so that's all for this video. See you in the next one. Now let's discuss some math instructions. So let's create a file called math.nasm, and let's once again use the global directive, global space underscore start and underscore start here, and let's hit enter, and let's write move instruction to move the value 2 into RAX register. Now we want to add 8 to this value, so we can use add instruction. So to do that, add RAX, 8. So we are adding the value 8 to the value 2 which is stored in RAX register. Now let's assume that we want to add the values that are stored in two different registers. So we can do that by using add the first register and the second register. In this case, we are using RAX as the first register as well as the second register. So the value that is in RAX will be added with its own value, and then it will be saved in RAX itself. So what this means is, currently after executing the second instruction, RAX contains the value 10. After executing this third instruction, 10 plus 10, 20 is going to be stored in the RAX register. Right, now let's see how subtraction works. We can use the instruction sub, and I'm going to use RAX, 5. So the value 5 will be subtracted from the value that is stored in the RAX register, and the resulting value will also be stored in the RAX register. So in this case, the RAX currently contains the value 20 and we are subtracting value 5. So RAX register now contains value 15. Now let's see another important instruction, which is increment. As I mentioned, RAX currently contains 15. Let's say you want to increment it by 1. We can simply use increment RAX. So now it is going to contain the value 16. Let's say we want to do it once again, increment RAX. Now we can also use decrement instruction to decrement the value by 1. So for instance, decrement RAX, decrement RAX. So we are using it twice. So ultimately, after completing the execution of this program, our RAX should contain 15. So let's save this program and assemble it and link it, and then let's load it in GDB. So I'm using nasm, math.nasm -o math.o -f elf64, and let's link it using ld math.o -o math, hit enter. Now let's load it using GDB. Alright, once again, let's set up a breakpoint at the entry point of the program. And we can clear the screen by using exclamation mark before the command. So it is going to execute the system command, not on the GDB shell. So if you hit enter, it is going to clear the screen. Another way of doing it is to type shell space clear. So once again, it is going to execute the command on the system instead of on the GDB shell. So let's hit enter. Look at that. So now let's type run. And these are the instructions that we have written in our assembly program. Once again, if you notice, the RAX is replaced with EAX. This could be once again because of the optimizations made. Before starting to execute these instructions, let's examine what we have in the RAX register. As you can see, the RAX register currently contains the value 0. So let's type SI. Now to check the value of RAX register, you don't have to always go to this register section. Instead, we can also type the command info registers. If you notice, the info registers command is basically showing us all the registers. Now let's assume that you don't want to see the output of all the registers. You want to see only the RAX register. You can do that, info space registers and RAX. There you go. it can be further simplified. We can just use I space R instead of typing the complete info registers, and we can type the register name. Look at that, we are still getting the same output. Now this is another way to examine the registers. So I'm clearing the screen and I'm typing SI. So the next instruction is going to be executed. What is the next instruction? That is add RAX, 8. The value 8 is going to be added to the value that is currently stored in RAX register. So currently 2 is stored there. So it is going to become 10, and 10 is going to be stored in RAX register after executing the next instruction. So let's type SI and let's type I space R RAX. Look at that, hex A, which is decimal 10. Now we want to add the value of register RAX with itself, and we want to store it in RAX again. So now after executing this instruction, RAX is going to contain the value 20. So let's type SI and let's use info registers once again, and look at that, hex 14 is 20. I can quickly show that using a calculator. I'm using this calculator here. I'm just typing 14 and let's move to decimal, and there you go, it is 20. Now the next instruction that we are going to execute is sub RAX, hex 5, which means 5 is going to be subtracted from the value of RAX, which is 20 here, and the resulting value should be 15. So let's type SI and once again examine the register RAX. Look at that, we have 0xF. Once again let's type 0xF here and let's check the decimal equivalent of it, and look at that, it is 15. Now the next instruction that we are going to execute is increment RAX. So this is going to become 16. Let's type SI and let's examine RAX. Look at that, it is 0x10 now, which is equal to decimal 16. So I'm just going to show that. Look at that, it is 16. Now we have one more increment instruction, which is going to increment the value stored in this register. So let's type SI and let's examine the RAX register, and look at that, it became hex 11. Now the next instruction is going to decrement the value by 1. That means we are going backwards. Now if I execute SI, it is going to become hex 10. Look at that. We are once again decrementing this value of RAX register. So let's type SI and examine the register RAX. Look at that, we have gotten 0xF into the RAX register once again. So this is how we can make use of add, sub, increment and decrement instructions in 64-bit assembly language. Now that we have discussed move instruction and add instruction, let's discuss some differences between these two instructions which can benefit us in exploit development. Let's assume that we want to move the value 2 into RAX register. I have shown you earlier, when moving small values into a register like RAX using move instruction, it is going to cause null bytes. So let's discuss how we can achieve this without causing any null bytes. So let's create a new program called nullbytes.nasm, and let's use the same old global directive, which is global start, and let's use start here, and let's use move RAX, 2. Let's save the program and let's quickly assemble and link it. dash O is missing here. Let's hit enter once again. There you go. Now let's use object dump and let's type dash M intel dash D null bytes. Let's hit enter. As you can see here, this instruction is causing null bytes. Now you have to remember that in larger programs, the RAX register may contain some values and you may not be able to store the intended values. So it is always a good idea to initialize the target register with the value 0. So let's first do that. Vim nullbytes.nasm and move RAX, 0. Let's assemble and link it once again. There it is. Let's once again use object dump and see what happens. Look at that. We tried moving the value 0 into RAX register, and even this instruction has caused some null bytes. So typically we can overcome this problem by performing an exclusive OR operation on a register with itself. So let's see how we can do that. I'm opening my nullbytes.nasm once again, and instead of using move instruction, I'm going to use XOR RAX, RAX. Now, regardless of what value RAX contains before executing this XOR instruction, it is going to become 0. Right? So let's assemble and link it and see if we have removed null bytes from this first instruction. I'm once again assemble and link it, and let's use object dump. And there you go. The first instruction doesn't have any null bytes anymore, but the second instruction still have it. So one way to do it, if you still want to use move instruction, is to use the sub-registers like we have seen earlier. So let's quickly do that. So instead of using RAX, I'm going to use AL, which is a sub-register, and let's quickly assemble and link it. Let's use object dump once again, and look at that, we have avoided null bytes in the second instruction as well. Right, this is a nice way of doing it, but there is another way, that is using add instruction. So what we can do is we can simply replace this move AL instruction by just using RAX, but by using add instruction. So we are using add RAX, 2. Essentially we are adding the value 2 to 0, so RAX ultimately contains the value 2. So let's save the file, assemble and link it once again. Let's use object dump, and look at that. Even the add instruction doesn't come with any null bytes. So clearly we can use add instruction as an alternative to move instruction if we want to avoid null bytes. I'm going to discuss how this exclusive OR instruction works in the next video, so see you there. In this video, we are going to discuss two important instructions, call and ret. Once again, to demonstrate the use of call and ret instructions, I have created a simple C program with the file name call-ret.c. So let's navigate to a directory called call-ret. Inside this, I have a file called call-ret.c. If you notice, the program is basically making a function call to a function called func, and it has 7 arguments. Once this function call is made, it basically executes the function definition. After the execution is completed, it returns back to the next statement in the main function, which is printf I am done, and it executes it. Now, like we did in the previous video, let's compile this and open it up in GDB and understand what kind of instructions are being executed while this is being done. So let's first compile this using gcc call-ret.c-o call-ret. There it is. Now we should have the binary call-ret. Now let's open it up using GDB. And I'm going to set up a breakpoint at the entry point of this program, which is main. Now let's run the program and let's go through the disassembly. I'm typing run. We are currently inside the main function. We are going to execute a bunch of instructions before making a call to the function named func. Now let's type si until we reach this push instruction. So I'm typing si, hitting enter once again, and there it is. Now we are about to execute this push 0x2bc instruction, which is at main plus 12. Let's observe the next few instructions to be executed. There is one push instruction, as you can see here, and there are a bunch of move instructions. We can probably do a disass main to better view this. There you go. There is one push instruction, and there are 6 move instructions which are moving some values. I'm not counting this move instruction for now. So we essentially have 6 move instructions and 1 push instruction. Now let's examine what these values are. 0x2bc, 0x258, and all this. So I'm just opening up a calculator, and I'm currently in hex mode. So I'm just typing 2bc, and let's check what it is in decimal. If you notice, this is 700. So let me type cat call-ret.c. If you notice, 700 is the last argument. How many arguments do we have here? 1, 2, 3, 4, 5, 6, 7. So the 7th argument is being pushed onto the stack. Now let's check what we have after the push instruction. Here it is, which is 0x258. 258 in hex should be 600 in decimal. So let's once again check the program. 600 is the 6th argument. And if you notice, this 6th argument is being moved into the register R9D. This is a sub-register of R9. Since the value being moved is not large enough, the R9D register is used instead of R9. So this is the 6th argument to the function. Next, the value 0x1f4 is being moved into the register R8D. This is a sub-register of the register R8. Once again, since the value being moved is not large enough, and thus the register R8D is used instead of R8. This is the 5th argument to the function. Next, the value 0x190 is being moved into the register ECX. This is the decimal 400, and once again ECX is the sub-register of RCX. Since the value being moved is not large enough, ECX register is used instead of RCX. This is the 4th argument to the function. Next, the value 012C, which is decimal 300, is being moved into the register EDX. This is a subregister of RDX. Once again, since the value being moved is not large enough, the EDX register is used instead of RDX. This is the third argument to the function. And similarly, we have 0xC8, which is being moved into ESI. This is a subregister of RSI. And once again, the value is not large enough. So the ESI register is used instead of RSI. And this is the second argument to the function. Now the last one, the value 0x5D12DA6FD005, which is a large decimal number, and it's being moved into the register RDI. Since the value being moved is large enough, this time the register RDI is directly used instead of a subregister. So this is the first argument to the function if you notice the C program. Here it is. Now these few instructions that we have just examined should give us an idea about how arguments are handled when a function call is made in Intel 64-bit processors. The first 6 arguments of a function are stored in the registers RDI, RSI, RDX, RCX, R8 and R9 respectively. From the 7th argument, they will be pushed onto the stack from right to left. Now, after all the arguments are handled, there is another important thing that we should notice. When we execute the call instruction at main plus 59, which is here, it will go ahead and execute the definition of the function. Once the execution completes, it has to return back and execute the printf statement in the main function. Then how does it know how to come back to the main function? Let's note down what we have on the top of the stack before executing call instruction. Let's also note down the address of the next instruction after the call instruction. So let's type SI. Let's type SI until we reach the call instruction. If you notice, we are about to execute this call instruction after executing the next move instruction. But before executing this, let's take note of the address of the next instruction after the call instruction. So I'm just copying it here and I'm pasting it here. And let's check what we have on the top of the stack. If you notice, we currently have the argument that we pushed earlier, which is 0x2bc, and I'm just pasting it here. Now let's type SI. Still the top of the stack is the same. Now let's execute this call instruction and let's see what happens to the top of the stack. I have executed the call instruction, and if you now observe the top of the stack, we have a different value. I'm just copying this and I'm pasting it here once again in the notepad right after the address that we have copied earlier. If you notice, the address that is pushed onto the stack is the same address that we have gotten, which is right after the call instruction. So what it means is, when the call instruction is executed, it has pushed the address of its next instruction onto the stack. So once the definition of the function is executed, it will return to this address by popping this value into the RIP register from the stack. So let's test our theory by completely executing this function definition. So let's do a single step. I'm typing SI multiple times. Alright, we are reaching the ret instruction, which is the last instruction in the function func. So I'm just typing SI once again, and there you go. We are at the ret instruction, and if you look at the next instruction after this ret, it is going to be the instruction or the address that we have just seen on the top of the stack earlier. But how does the processor know that after executing this ret instruction, it has to go to this address? when the ret instruction is executed, it is going to pop the value which is on the top of the stack into the RIP register, and then it will execute that. If you notice the top of the stack at this point of time, it has the same address, which is the address of the next instruction to the call instruction. And when we execute this ret instruction, this address is going to be popped into the RIP register. So let's type SI and look at that. RIP register now contains the address of the instruction, which is right after our call instruction. So that's how functions work. To give a recap, in this lecture we have seen how functions work and how registers and stack are used to manage the arguments of the function, and then we have also seen how the return address is placed on the stack. So primarily we learned a few things in this lecture. How arguments are managed using registers and stack when a function is called, how return value is placed on the stack when a function is called, and we have also learned how the return address is popped into the RIP register when a function is returning from its execution. We have also understood that ret instruction always pops the value from the top of the stack into RIP register to be able to return to the next instruction of the calling function. That's all for this video. See you in the next one.